These are your instructions. In general, you just need to follow a PowerPoint. Please make sure the sound is turned up on your device so you can hear the narration. On some of the slides, there are instructions for you in the yellow boxes. And don't forget, if a slide asks you for homework, send it in via Show My Homework. And if a slide asks for Educate to be completed, don't forget to do it by the date given.
At the end of this lesson, you should know the definition of momentum as mass times velocity. You should be able to use the idea of momentum to describe the motion of objects, and you should be able to explain and apply the conservation of momentum. All objects that are moving have a property called momentum. This is a measure of how difficult it is to stop a moving object. Now, the first key point you need to know from this definition is that objects that are not moving have zero momentum. The momentum of an object can be calculated using this equation. Momentum equals mass times velocity. In shortened form, it's written like this. P equals mass times velocity, m times v. The P is for historical reasons. In this equation, the mass is measured in kilograms, the velocity is measured in meters per second, and because you're multiplying mass times velocity, momentum is measured in kilograms meter per second. You're not given this equation, so you need to memorize this one for your exam. So let's have a look at a quick work example. A car has a mass of 1,000 kilograms and is not moving. What is the momentum of the car? I hope you remembered that any object which is not moving has zero momentum. So in this case, the car is not moving, its momentum must be zero. Now let's have a look at the same car, but the car is now moving at 20 meters per second. Calculate the momentum of the car. So our formula is momentum equals mass times velocity. In shortened form, P equals m times v. The mass is 1,000 and the velocity is 20 meters per second. If you multiply them together, it gives you a momentum of 20,000 kilograms meter per second. If we look again at this formula, P equals m times v, it should be apparent that because you're multiplying mass times velocity, objects with more mass will have more momentum, and objects that are moving faster will have more momentum than objects that are moving slower. The other thing that you need to know about momentum is that it is a vector quantity. That means it has a size and direction as opposed to scalar quantities which only have size or magnitude. If two objects of the same mass are moving in opposite directions but at the same speed, i.e. their velocities are different, the momentum of each object will be the same magnitude but will have a different direction. To allow for this, we sometimes add a plus or a minus to indicate the direction of the momentum of moving objects. Have a look at this piece of apparatus, which is something called a Newton's cradle. What does it tell us about the momentum in collisions? Newton's cradle is useful because it shows us how momentum is transferred in collisions. So the momentum is passed from one object to the next, to the next, to the next. This leads us on to the idea of something called the conservation of momentum. If two objects collide or interact, the forces acting on them are the same size but in opposite directions, and the same is true for the momentum of each object. What this means is that the momentum lost by one of the objects will be gained by the other object. So whenever two objects collide or interact, the total amount of momentum is conserved. Now, there is a condition for this, and that condition is that the system you're looking at has to be a closed system. So a closed system is when you're focusing only on those objects and you're not allowing for any energy or matter to be transferred to the larger environment. The idea of conservation of momentum is easier to understand if we have an example. So let's have a look at these two trolleys, a blue one and a green one. What happens is they collide and they move off together. Now here's some information about the trolleys. Trolley A has a mass of 3 kilograms and a velocity of 8 meters per second. So its momentum can be worked out using momentum equals mass times velocity. 8 times 3 is 24 kilogram meters per second. Now trolley B, the green trolley, has a mass of 5 kilograms and a velocity of minus 4 meters per second. Now that means it's moving in the opposite direction of the blue trolley. But we can still work out its momentum by using mass times velocity. 5 times 4, but this time the 4 is a minus 4, gives you a momentum of minus 20 kilograms meter per second. So now you have two trolleys and two masses, two velocities, and two total momentums that you worked out before. After the collision, these two trolleys have stuck together. So now the new mass of this item, this object, is 5 kilograms plus 3 kilograms is 8 kilograms. The conservation of momentum tells us that the total amount of momentum after the collision is the same as before. So if we add together the total momentum before the collision, we get 24 plus minus 20 is 4 kilogram meters per second. After the collision, that momentum has to be conserved. The mass of the new object is 8 kilograms. The momentum is 4 kilogram meters per second, exactly the same as it was before, which means we can use momentum equals mass times velocity, rearrange it to give us velocity equals momentum divided by mass. Now we know the momentum after the collision and we know the mass after the collision, so we can work out the velocity. Examiners like to set questions on conservation of momentum, and there's lots of instances that they can use. So let's go through a few popular ones. One is billiard, pool, or snooker balls. So you have objects with a given mass colliding and moving off either together or separately in opposite directions, depending on how the question is phrased, but it is a question about the conservation of momentum. Another popular type of question involves explosions. A bomb, which is originally at rest, has zero momentum because it isn't moving. After the explosion, all the bits of it are moving in different directions. But if you add up the total momentum for all of those parts, it will add up to zero, which was the original momentum. Another popular type of question involves either a gun or a cannon. So what you have is initially the system is at rest. After the weapon is fired, the bullet or cannonball moves in one direction, which means that the gun moves in the opposite direction. Again, it's the application of the conservation of momentum. Your last task for this lesson is to answer the following 5 questions on momentum and send your answers to Mr. Rahman by Friday the 17th of July. Thank you.